All right, so let's continue. Uh, if you recall that what we have been doing is carrying out synthesis, given the description of the problem. We've been looking at how we can design a finite state machine or a RTL system. And very early on, we discussed that uh, when you design something, you need to verify whether the design is correct or not, and you need to evaluate its performance. And so, for example, let's say we have a design like this, and if we need to check whether, for example, given a description, we have arrived at a data path and a controller and all that, and we need to check whether this particular design does what it is intended to do. And I was mentioning in the last lecture that what you can do is you can take a design and then describe it in a hardware description language, an HDL, hardware description language, whether it's VHDL or Verilog, and then you can simulate it. Now, if you think about simulating a data path like this, what we are talking about is not circuit simulation, where you're talking about voltages and currents and all that as a function of time. What you're talking about is more of logical simulation. We are talking about how logic values, ones and zeros and all that, how they evolve over time. Right? If you're doing logic simulation as a function of time, then so a important part is, when you're using a tool like VHDL and you're simulating it, you need to understand how this particular tool is really simulating. What is it doing? When we say that we are simulating this particular circuit to check its correctness, what exactly are we doing? How are we simulating? So the purpose of our discussion today is just to introduce you to some of the basics that are there in so when you use a tool, you're not using it as a black box. You have an understanding of what really is going on. And you'll also see why, for example, the simulation that you're doing is, for complex circuits, we'll see that if you want to know whether your design meets the timing constraint or not, it becomes very difficult. The simulations are, especially when the design is complicated, the simulations are expensive, they take time. And we need to go to, I've been mentioning earlier also, we need to find the worst case paths and all that to look at timing here. Anyway, so let's very quickly look at how this logic simulation may be done here. All right, so the first part of logic simulation that I want to discuss is not look at delays at all. Each one of these things that you see here will have delays in them. But first, not talk about delays and do a logic simulation just to check whether your circuit is functionally correct. It performs the function that it's supposed to do. Okay? So this is what we mean by a zero delay simulation, in the sense that once I apply an input to a gate, the output immediately becomes available. All right? So we are just simply checking whether, if you have designed an adder, does it really add or not? The second part to it, of course, does it add within the constraints that you want? Does it add within a few nanoseconds and things like that? That's the second part, which is the timing part. But the first part is it functionally correct? All right. So basic issue is, given the input, what is the output here? So again, to illustrate some of these things, we take very simple examples. So the issue that we are asking is, we have three inputs, I1, I2, I3. And what we would like to know is not just the output here, but we would like to know the values at every place here. Values of output here, basically all the values. Just like in circuit simulation, you know that you want all the node values or node voltages and currents and all that. Similarly here, we are looking for all the, at every node, we are looking for what the logical value is as my input vector changes here. So the issue is, we want to know as the input vector I1, I2, I3, when you apply a particular input vector, we would like to know the states of all these lines here that you see here, 4, 5, 6, 7, all these lines we would like to see how they change here, okay? So how do we do this, okay? All right. Now note that each variable is, suppose I want to compute the output here. If I want to compute the output here, then I know to compute the output here, I need the values at line 5 and line 6. Right? And to compute the value at output here, line 5, I need the value at line 4. So which means that if I want to compute the logical values at these different places, I have to do it in a particular order. I can't just start and calculate, determine what the value at this particular line is unless I know what the previous lines are. So evaluation has to proceed in a particular order. All right. And this particular order that we are talking about is obtained by what we call as dividing the circuit into levels. This is called levelizing the circuit. So for example, when I have a circuit like this here, we can define that gates A and B are level 0, in the sense that to evaluate them, I only have to know the inputs. Okay, so they are level 0 here. I can evaluate A because once I'm given the input, I can evaluate gate A. And similarly, once I'm given the inputs, I can evaluate B. So A and B are level 0. C is level 1. It's level 1 because to evaluate it, I have to know the values of the previous level. I have to know what the value of gate A is in order to evaluate C. So that's why C is level 1. And D is level 2. Because to evaluate D, I have to know a value of a gate which belongs to the previous level here. So we take up a circuit and we divide it up into levels. That's what, I'm just describing one very simple way by which you could do logic simulation is take your circuit, divide the circuit in the form of levels that you see here. So basically level of any gate is the level, maximum level of fan-in. Fan-in means any of these lines plus 1. That's how you assign a level here, right? So the level of this particular gate, which means output line 7, will be maximum of these. So you evaluate these input lines here, whatever is the maximum level, which is in this case here, plus 1, and that's how you arrive at here. Now, the next thing that you do is, if you want to simulate this netlist that you are seeing here, this gate netlist, one way, I'm not saying this is how it is done, but one way in this VHDL or Verilog, I'm not saying that, we'll come to that later. One way in which you can do that is take this particular netlist and convert it into a code. In what sense? We have already levelized the circuit. So for example, I can convert it into a sort of a subroutine. For example, AB. So I have a call not V4, V2. In the sense, this is the input, V2, the subroutine will return the value V4. So I can have a small subroutine or whatever, call not here to evaluate gate A. So I'm going to evaluate AB first. Call and's output is V6 here, V2 and V3 are the inputs here. So note that when I write, the whole circuit is being converted into a code. So when I come here, I already know the values because I've levelized the circuit. So when I want to determine V6 here, I already know the values V2, V3 because the previous ones have already been simulated. Those pieces of code have already been executed here. So one can take the circuit, after levelizing it, convert it into a code. Right? So a code like this, call not, there are many ways of coding it. So call not, call and, call all. And the whole circuit is described in the form of a code here. Right? So the whole code is simulated for each new vector. So every time you get a new vector, you simulate this particular code. You run this particular code and obviously all the values will get updated. V2, V4, V6, V1, and you will have that value. If you're wondering how do I do for, many of these circuits have feedback. So what is suggested is that you can cut the feedback line here at this particular point, and the circuit is iteratively solved till you obtain convergence. So you assume a value, let's say some values here, and solve the circuit the way it is said here. So you will get some values here, update these values here again, solve it again till you find things converge. And that's how, if there's any feedback loops, that's how you can handle it through the same means here. Very simple. All that we are saying is take the circuit, levelize it, and convert it into a code, and just simulate it for every vector, for every input vector here. Except that is difficult to, when you use this approach, and if I want to extend it, where I have delays in it, then you can see that I have a problem. We levelized the circuit, and we said this is the order in which we are going to compute. But if you have delays, then delays means the gates have to be evaluated according to how much delay they undergo. It's not simply a simple level that we are talking about. And more seriously, the problem is that it's very inefficient simulation. Okay, let me illustrate that. It's very inefficient simulation here. All right, look at this particular part here. Let's say we start from 0, 1, 1. This is our initial, 0, 1, 1 is our initial input vector. All right. Now, how will our simulation go? 0, 1, 1, if I apply, my gate A is going to be simulated, so I get 0 here. These are going to be simulated. When this is being executed, I get a 1 here. Then I'll execute gate C here. So 0 and 0 here, so it will give me 0 here, and then 1 here, right? So that's how, as I run through my code for this particular input vector, all these values will be generated here. But suppose now from 0, 1, 1 to I go to 1, 1, 1. According to us, what will happen? For 1, 1, 1, again the whole code will be executed again, right? But what really happens here? At any given time, you can just from 0, 1, 1, if I go to 1, 1, 1, you'll see that in this particular, even in a simple circuit, you'll find that only a fraction of the gates are changing states. In fact, for larger circuits, people claim that when you take a large circuit, and let's say there is an input vector which is already applied, and then you go to a new input vector, right? Typically, only 2 to 10% of the gates are active. Active in the sense that they have changed their states, or one of their inputs have changed values. Okay, only 2 to 10%. But what does this method do? For every new vector, you have 0, 1, 1, you execute the whole long code. And then you get a new vector, 1, 1, 1, you execute again the whole long code here. Now all this, why are we talking about you execute the whole long code? Because remember, our circuits are not as simple as this. We're talking about circuits with hundreds of thousands of gates. Huge circuit. And we would like to evaluate a circuit as the number of input goes up. Remember, if you have 3 inputs, then you have 2 to the power 3 possible input values. If you have 20 inputs, you have 2 to the power 20. So, the whole issue is one of complexity. As circuits become complex, as the number of inputs become complex, I like to simulate it maybe millions of times. And if for each vector, I have to simulate this whole long code, then it's not very efficient. It's going to take a lot of time. And then when we examine it, when we examine a circuit like this, we find that when you go from one vector to another vector, typically a small fraction of the gates are only changing, or they're active. So how do we simulate? So the idea is that this is not a very efficient way. It's a very straightforward way of simulating. Take a circuit and convert it into this code and simulate it. That's a very straightforward way of doing it, but that's not efficient. That's not how your logic simulators, which are under VHDL and Verilog, that's not how they work. The idea is simulate only those gates which make sense on whose input an event has occurred. It makes sense that if by changing, going from one vector to the next input vector, if there is a change in the input of any of the gates, then only you should simulate it. If there's no change in any of the inputs, that means that the gate is inactive. Don't simulate that particular one. And this is especially important because, as I said, statistics show that only a small fraction of the gates are at any point active. So imagine if you have to simulate, even in the worst case, 10% of the gates, you're getting a 90% saving. Right? So the whole idea is then what we are talking about is a simulation which we call, you'll hear the word very often, event-driven logic simulation. That, what do we mean by event-driven logic simulation? Well, first of all, what do we mean by an event? Event is when you take a gate, let's say, and a change in the value of one of the inputs has occurred. So for example, if we look at a change from 0 to 1 has occurred, which we then say is an event has occurred on line A. On B, no event has occurred, right? So what we are saying is, if an event occurs on any of the inputs of a gate, simulate it. Simulate that particular gate here. So our simulation is going to be driven by events. Simulate only, don't just take a whole circuit and put it into a form of code, and irrespective of what happens, blindly keep on simulating for every vector. Don't do that. Do it more intelligently and simulate only those gates on whose input an event is occurred. All right. So for example, you can see here, this illustrates the event-driven logic simulation here. So this is the initial state of the lines here. Initial input is 0, 0. 0, 0, and you can compute all the values of all the lines that you see here. So we have basically, this is line 1, and we have 7 lines here. So it's a 7 element vector here. So this is the first thing here. An event has occurred on 0 to 1. Right? So event occurs here. So when we go from 0, 0 to, let's say, 1, 0. So an event occurs here. So what do we simulate? When an event occurs here, we simulate input to this particular gate has, an event has occurred to this. So we simulate A. And an event has occurred on the input of this one. So we simulate gate C. We don't simulate B because no event has occurred here. We don't simulate D because no event has occurred here. And we don't simulate E. We don't do A as a first step. Okay, the values will not become available in one step. When you do event-driven simulation, things cascade. When an event occurs here, this may cause an event later on here, and then it may cause an event later on. So you have to do it in multiple steps here. Okay, so an event occurs here, so you evaluate A and C. So what will we do when you evaluate A and C? So this goes 0 and 1 and all that, you update your line values here, 4, 2, 3, 6, all the line values that you see here. So you will simulate C and you will update 5. And you will simulate A and you will update the line of the value of 3. And you're not going to do anything with the rest of it. Okay? So the new states are here. In the next case, what you find is because 0 to 1 you went, so this particular line goes from 1 to 0. An event occurs here on D. And similarly, an event occurs on this particular line here. So what you do is you simulate D and E. So in the next, no event has occurred here. So in the next step, no event is here, no event is here, but an event has occurred on the inputs of these two gates here. So I simulate D and E. And then evaluate what happens here. Okay. So the order of the simulation then goes AC first and then DE. And then I arrive at the final value. When do you reach steady state? When no events are occurring on any of the lines. Then you've reached the steady state and you have the final value. So in this very simple case, what we have done is for a change like this, when you go from 0, 0 to 1, 0, what you see is that we simulated A and C first, then D and E, and we arrived at the final values. The simple example is saying I did not simulate gate B. Right? There is a saving. You don't see much of a saving because it's a trivial example. But you're able, but even in this simple case, you're saying that I need not simulate gate number B. It's not required. No event occurred here, and therefore I did not simulate this. So the way this works is the following. The algorithm works, prepare an initial event list. The first step is an event list. Where does the event list start from? From the input. An event has occurred. So prepare an initial event list, evaluate elements on the fan out of lines on which the events have occurred. Find out what are the gates that are connected to those lines on which an event has occurred. And evaluate those elements. And when you evaluate those elements, what you do is you are creating a new event list. A new event list, and then you keep on executing it till you find that your event list is empty. Right? And what is being claimed is that even though you may be doing it in multiple steps, and as we'll see, some gate may get simulated more than once, even then it's way superior as compared to the previous method where you're simulating the whole circuit for every input vector. Okay? So this is basically illustrating, you can go forward. So when the same thing that I illustrated 0 to 1 and 0, 0. So what you do is my event list is what? Line 1 has gone from 0 to 1. Right? That's my initial event list, prepared from the input vector. Line 1 has gone from 0 to 1. Now evaluate elements on the fan out of line 1. What are the elements on the fan out of line 1? Line 1 is connected to A and C. So evaluate A, and then you update the value. V3 goes to 0 here. Evaluate C, V1 is 1, V4, and evaluate here. Update the line values. Okay, all the line values are updated. Where has an event occurred? You prepare a new event list. Line 3 goes from 0 to 1. Line 5 goes from 0 to 1. New event list. Now you look at the outputs. What is connected to line 3? Line 3 is connected here to D. So you'll simulate D. Line 5 is connected to E. So you'll simulate E and generate a new event list. And that's how you keep on going. Okay, straightforward method here. All right. So this was the point that we raised. A gate may be simulated more than once. It can happen. So let's see here, 0, 0, and these are the initial values. Note, 0 here, 1 here, 0, and all the initial values are given. Suppose I go to 1, 1. All right, what happens? Which gates are simulated? So I start from 0, 0, and I go to 1, 1. Where is the immediate event has occurred on? Obviously here and here. So which gates are simulated? A, D, C. These will be simulated, right? A and D and C, both. B also. So these are the gates that we simulate, right? A, B, C, D. What are the changes that occur after you simulate? Note, these were 1, 1. These become 0, 0. Right? After you simulate, these become 0, 0. And these become 1, 1. After you simulate these, you have to simulate A, you have to simulate B, you have to simulate C, you have to simulate D. And these are the changes that occur. Where do events occur now? Huh? No event on A. So what happens is C, D, E. So event has occurred at this. So evaluate C, D, and E. When you evaluate C, D, and E, what happens? This becomes 0, 0, 0 here. And where do the events occur now? No changes here. Only E. So you evaluate only E here. And then finally, you get the values here. Right? So in the process, which gate did we evaluate more than once? Some of these gates that you see, we did evaluate more than once. Okay, so it does happen. So it appears as if, well, in the other method, you may say, well, other method for a particular input vector, I'll evaluate a gate only once. Right? But remember, in this, we are only simulating a fraction of the gates. And a few gates may get simulated more than once, doesn't matter. It still is far superior as compared to the previous method that are there. Now, how do you incorporate delays in it? So far we only said that the whole thing is simulated in an event-driven manner. Now, it's fairly easy to incorporate delays also. So far we only said, for example, we said that there is an event list. So now what you can do is you can take the event list and actually generalize it into what we call as a timing list. So you say not only that an event has occurred, but you schedule the event. You say event has occurred at t equal to 0 nanosecond. Right? And then when you evaluate elements here, for example, you evaluate this particular element, so you will find that an event has occurred on line 3. Right? So when you evaluate the elements on this particular one, you say event has occurred on line 3. Line 3 goes 0 to 1. But depending on the delay, you say it goes at 2 nanoseconds. And simulation proceeds at some, discrete intervals, let's say at every 1 nanosecond. So you do it at 0 nanosecond, then 1 nanosecond, and 2 nanosecond, and 3, let's say. So you look at this new event list, and the event list now is a timing list, and it has this information also. So you evaluate it, and you say, well, at 2 nanoseconds, then this is there. This event has occurred. And then accordingly look at what is connected to this particular line here, and then evaluate them. And as you evaluate them, you will find, well, let's say gate D gets evaluated, and gate D has a delay of 4. So then you will update and you'll say gate 6, line 6 needs to go from some state to some state at maybe 4 plus whatever, 6 nanoseconds or so. So the whole idea is just from an event list, it becomes a timing list. And then you keep on processing the timing list till you find that there's no activity. The timing list is empty. Okay. So anyway, these are similar things. If we only wanted to verify the functionality of the circuit, all we had to do was simulate a gate. And simulating a gate requires what? Basically simulating a NAND gate or an AND gate and all that is a simple logical operation. All you're testing, for example, an AND gate, all you're testing is whether any input is 0 or not. If any input is 0, you know that output is 0 here. So computing or a NAND gate or an AND gate is actually very simple. It doesn't cost much. But when it comes to a delay, it becomes expensive. The simulation becomes expensive because what do you have to do? You have to do an addition operation. This, for example, is at 2 nanoseconds. The next line has to occur at 2 plus 3.2, 5.2 nanosecond. So when you have to compute and you have to do an addition, 5.2 and 6.3 and all that, you have to carry out an addition. An addition is a far more expensive operation. So when you only want to check the functionality of the circuit, don't bother about the delays, just run your simulation and everything is fine. But when you want to check some timing aspects here, the simulation will get slowed down because of all these additions that have to take place. All these values that have to be computed, at which time 2 plus 3 and 4 and 5 additions have to be done. And additions are computationally far more expensive than a simple logical evaluation, and not, nor, and things like that. Okay. So even, timing simulation then becomes expensive. Now, when you do timing simulation, you have to incorporate delays in it, right? And there are different ways of modeling delay. One of the phrases when you look at logic simulation, some of the simulators will say you can enter delay in the form of what is called a transport delay. Now, it's fairly simple. The idea is that if, let's say, you take an inverter and a transition occurs at time t0, then the output, of course, will go from 1 to 0, and the transition occurs at whatever is the delay here, t0 plus 5, after a certain delay here. So basically, the same signal is transported here with a logical change, but after a time, certain time, which is a delay here. Now, as I was saying, delay involves not just addition and all that. Now, how do you compute what is this 5 here? So you are saying that when I encounter an inverter, I should have the output which is t0 plus 5. How do you calculate this 5? Usually, as I've been showing here, the delay is made up of two parts. There's an intrinsic delay, and there's a delay which depends on the fan out. If I have a one inverter connected here, this particular inverter will have one delay. If I have 5 inverters connected here, right? So the capacitive load on this one is much higher, and the delay would be something else. So I have to compute the delay also, depending on the circuit. How much is the this thing here? How much is the So these computations and all that, they further make timing simulation more complex. I have to evaluate how much delay is there for this particular gate, and then of course, as I said, during the simulation you have to create timing list and all. So one of the ways in which, very simple ways in which you incorporate delay is, all that you say here is that this transition is occurring at time t0, and when you say transport delay is 5 units, then you say, well, the transition will occur after 5 units. Now you'll see that there's a little bit of a problem here, because this is a simplified, abstract view of really what is happening. What actually is happening when I give a, let's say, 0 to 1 or 1 to 0 kind of a thing, and the output does not respond like this. The output does not respond in a square wave manner here. The output will respond something like this here, right? And what we are doing is, the output is actually a voltage. Input is also a voltage. Even if the voltages inputs are sharp, let's say, with very sharp rise time and fall time, the output is not going to be like that. And so what we are saying is, when we draw like this, we are actually taking a complex waveform and we are approximating it, in the form of a square, saying that, well, after a while, the output can be considered as logical 1. Below a certain point, the output can be considered as a logical 0. So you're doing that kind of a transformation to arrive at that. Now, this point is important because next, look at this issue. If you say I have only a transport delay, right? I have only a transport delay of 5 units. If you say that in your circuit, then let's say this goes down and this goes up here. So what happens is, if this goes down at t equal to 0 and transport delay is t0, this will go up at t equal to t0. And then depending on the pulse width, this will go down after whatever, the delay that you see here, right? Now, problem occurs is, what if the pulse is very narrow? If the pulse is very narrow, if you just had a transport delay, all that would happen is that whatever happened here, it would happen after 5 nanoseconds. Whatever happened here, it will happen like this. But this is not what happens in reality. If the pulse is very narrow, note that pulse is very narrow, the output doesn't get a time to go back. Remember, the output was starting from here, going back to VDD and then falling. If the pulse is very narrow, the output doesn't get a chance to go to VDD. In fact, if VDD is, let's say, 3 volt, if the pulse is very narrow, it may just go to 0.5 or 1 volt and then come down, because the pulse is so narrow here. It never went to logical 1. It never went to logic 1. Right? So this picture will give you incorrect. If all I say is that my gates have a delay called transport delay of 5 nanoseconds, then if I give a pulse like this, it will produce a pulse like this here. But in reality, if I give a pulse like this to my inverter, the inverter never goes to logical 1. In fact, all that it would show is flat, logic 0. The transition was never made. So what this is pointing out is a simple delay model of saying that I have something called a transport delay is insufficient. Insufficient because it's going to predict wrong values. If you have pulses like this, it will show something of this sort where it never happens here. Okay. So what we have is, in addition to transport delay, people use a delay called inertial delay. So gates have a kind of, if you think about it, it's like if I apply a very small pulse and the output didn't respond. Right? So it's as if my gates have a kind of an inertia. And if input pulse is too narrow, then the gate would not respond to it. Right? This is what we are saying. And therefore, we are modeling this by defining a inertial delay. So for pulse width larger than inertial delay actually acts like a transport delay, the original delay here. For smaller pulse width, it rejects the input altogether. So you may model the delay of a gate not in terms of a transport delay, but you may model it in terms of an inertial delay. So for example, if I have, let's say inertial delay is 10, and some units, 10 nanoseconds. If the input is like this here, and note that the pulse width is 15 is larger than 10, the output is just a delayed version with a logical inversion, right? So after 10 units, this will go down, and it's just a reproduction of this. But if you give like this here, and inertial delay is 10, then the output is 1. So this is a more accurate reflection of what really happens in circuits. A delay cannot be just simply that no matter what happens, you delay everything by 10 nanoseconds or 15 nanoseconds. So inertial delay is slightly, is a better model. But again, remember, these are all abstractions. These are all abstractions. The real delay values are at the circuit level, where you actually have the voltages and all that are coming. So even though this is more accurate than the previous one, it's a little bit harder to define what is that value below which it will be really rejected, that it will be considered as 0. All right. The other thing is, as I said, I don't want to go into the details of it. I just want to give you an idea of what is really going on inside a logic simulator. Okay, so we saw that most of these logic simulators will be event-driven simulators, and concept of a delay is a bit problematic. Inertial delay may be better than a simple transport delay. The other thing is, the logic simulation has to be done not just with zeros and ones. Logic simulation has to be done with what we call as multi-valued logic simulation in order to get a good understanding of what is really happening in my circuit here. And there are many reasons why I need more, besides 0 and 1, I need more variables, right? For example, when I power up, the state of the flip-flop is not known. I don't know if you have designed a circuit in such a way that when you power up a circuit, a clear or a reset or a signal goes to all the flip-flops and clears it or resets it, then it's fine. But if you don't have that, remember, if you do that, then you have a clear line running all over your 100,000 or whatever flip-flops and all that are there. So that's expensive. But if you don't do that, then remember, once you power up, you don't know where the flip-flops are. It may be 1 and 0, but you don't know where they are. They are starting from some unknown state here. It may be that you've designed a circuit in an incorrect manner, in such a way that there is a line, one gate is trying to drive it to 1, and the other gate is trying to drive it to 0. Right? One gate is trying to drive it to 1, the other gate is trying to drive it to 0. The whole purpose of logic simulation is to find out whether things are incorrect or not, whether things have been rightly done or wrongly done in your circuit. So let's say one is driving to 1 and the other is being driving to 0. What will be the state of that line? I don't know. Right? So we may want to introduce another variable called u, which is unknown. We don't know what it is. Okay. So again, if you look at it, we've been talking about a delay of a gate. Now, delay of a gate is not something I've said 5 and 10 and all that. Delay of a gate can vary within a limit. Why does it vary? Well, because the mobilities vary, the threshold voltages of the transistors vary. The temperature of that particular place where your inverter is located may not be room temperature. So temperature may be different. So as a result, there is uncertainty in the delay values. So when you give a very nice pulse like this, I don't know when it is going to zero here. Is it going to zero here or is it going to zero here? Why? Because of the uncertainty in delay. I don't know the precise values of the delays. So there's a time when the value is uncertain. I don't know whether it's 1 or whether it's 0. Similarly, when it's going up, I don't know whether it's 0 or 1. Okay. So what we may see here is that through these simple examples I'm trying to illustrate is that 0 and 1 is not enough for you to do logic simulation. What you need to do is introduce another variable, which is u, that I don't know, unknown state, right? And then what we need to use is 3-valued Boolean algebra. So for example, if I have an AND gate you're familiar, so AND gate can now, each input can have 0, 1 and u, and 0, 1 and u. So if it is 0, obviously, and the nature of the AND gate is that all of them will be 0. If it is 1, this is obvious. If it is 1 here and u here, then the output would be u. I don't know what it is. And if it is u here, if it's 0 here, fine. Otherwise, is u. Right? So this may have a value that you may do a 3-valued Boolean algebra. And you may simulate the gates with those 3 values that are there, 0, 1 and u. But even that may not be enough. I may want to do a 5-valued simulation. 5-valued logic simulation. Why? Well, now note what the values are. I have 0, 1. I've introduced another variable when the input is making a transition 0 to 1. Another when it's making 1 to 0. And the 5th one is u. Now, why am I doing this? Well, consider this. When the input is going from 0 to 1 and when it's going from 1 to 0. Right? Look at this A and B. B is going here and A is going here. What is the state of the output? The state of the output, as you can see here, the way I've drawn is A to 0 and B to 0 here. The state of the output is, well, initially 1, 0. Finally is also 1, 0. So it should actually be 0, 0, right? But in between, it may go to a 1 here and then 0 here. Glitches and all that we call. Another word for this is, it's a static 0. And there's a formal name for it. It's a hazard. Hazard means it can cause a problem somewhere in your circuit, right? It's a hazard in your circuit here. Static 0 means normal value is 0. It should have stayed 0. But why? Because the inputs to A and B arrived at different times. Input at A and B will arrive from some parts of the circuit, and A may get more delayed as compared to B, and therefore you may get a value like this here. So the idea is that if you want to catch these things, does a static 0 hazard occur in my circuit? Well, you may want to do a 5-valued simulation where it allows 1 to 0 and 0 to 1 and all that. It says when 1 to 0 and 0 to 1, there's a possibility of an unknown state here. In between, there is a possibility something happening here. So people may want to do a 5-valued simulation here. Let me illustrate this in a little bit more detail here. So consider the following. 1, 0, all the values are given here. Okay? All the values are known. 1, 0, I hope these are all correct. So now let's change A. A goes from 1 to 0. What happens? 1 to 0. This immediately reacts. Right? 1 to 0, this is directly connected. This will go down. Right? After these dotted line shows when the transition occurs at what time. And the solid line shows that after a delay, this will go from, because this went from 1 to 0, this will go from 1 to 0 here. But then, what happens here? This goes from 0 to 1 after a longer time. Why? Because there's an inverter here. There's an inverter here, so this goes 0 to 1 here. And then as a result of this, you get a glitch here. A static 1 hazard. Now, I've deliberately put an inverter. This may not be an inverter at all. All that I may have is a longer line which goes to this particular gate here. So it may be the same input A which goes to a longer line here, and longer line means more delay on it. Or it could be a AND gate as compared to this one. This AND gate has more delay as compared to this. No two AND gates, even if you have, as I've been saying, even if you've designed them in the same manner, will have the same delays. Because of variations in threshold, mobility, temperature, all kinds of things that are there, the delay of this may happen to be more than this. So you will end up getting a static 1 hazard here. Now you can take actions in order to prevent such static hazards in your circuit. For example, if you look at this particular circuit that is there here. This particular circuit is A bar B plus AC bar. A bar B plus AC bar. So the way it has been implemented is, we have taken this, and these are the two terms, and we have implemented it. Now if I add, you can see here, I can add a redundant term here. Nothing will change in your expression. It's the same functionality. But if I take one more term here and add this BC bar, and I get a new circuit with an additional one, you can verify that this will not have a static 1 hazard. No static 1 hazard will occur here on this one. On this one it will occur. On this one it will not occur. You can do that, the same thing with A going here, and you can check that a static hazard does not occur here. Okay. So the point that is being made is that once you simulate your circuit with multi-valued logic, and hazards are potentially likely to occur here, you can intervene and do things and modify, add some redundancy and all that, and eliminate some of those things that are. Okay. Now, by the way, even I've been talking about static 1 hazard and static 0 hazard. 1 hazard is where its value is expected to be 1 and temporarily goes to 0. You may get a dynamic hazard also. In the sense is 1, it has to go to 0, but it goes 1, 0, 1, 0. Things like that may be happening in your circuit too. These are called dynamic hazards. Dynamic hazard means the output changed state more than once. 0, then 1, and then back to 0 there. Even these things may be happening in your circuit. And if you're interested in detecting, are dynamic hazards occurring in my circuit? Where are they occurring? Well, you'll have to do all these multi-valued simulations. And your VHDL, for example, does a multi-valued simulation and provides the following values here. VHDL, when it does a simulation, doesn't take only 0 and 1. In VHDL, there is U. There is a logical state called U, uninitialized, unknown. There is an X. I'll just quickly explain. Forcing unknown. Forcing 0 and forcing 1 are like what you're familiar with, 0 and 1. There's a high impedance state. We know that, you have tri-state and all that. Some state may be high impedance. So that's something which is required here. There's a weak unknown. There's a forcing unknown and a weak unknown and a weak 0 and a weak 1 and a don't care. So 9 valued simulation is being done in your VHDL, and I'm sure something similar is being done in Verilog. So every gate is being evaluated with a 9 valued simulation. All right. What is this? This will become more clear later on when we come to MOS transistors here. But the basic idea is, when you take a NMOS and when you apply a 1 to the gate of an NMOS, then the output, NMOS is very good in, propagating 0 to the output here. And we say it's a strong 0, forcing 0 here. PMOS is very good in propagating a high value VDD to the output here. But when you use a NMOS to propagate to a node, high value here, you don't get you get a 1, but it's not a good one, in the sense it's value, if you have VDD here, you'll get VDD minus something. So it's a lesser voltage here. So we call it a weak one. Similarly, when you take a PMOS and you connect it, when you put a 0 here, PMOS is on. 0 will go here, but the value at this point will not be 0 volts, but it would be maybe 0.5 volt or 0.7 volt or whatever. So we say it's a weak 0. Now, why are we having to do all this? Because we are doing logic simulation. If we were doing circuit simulation, we have the precise values. What is the value of the voltage here and all that? At the logic state, we don't have the values. voltages and all that. So somehow, that is being, one is attempting to capture some of those things by saying, well, I have a weak 1, I have a weak 0, and things like that. Okay. So, all these simulations are being done with a large number of possible variables which are listed here. Okay, how do we resolve? I'll leave all that with you. You can have a line which is being driven. You have a line, somebody is driving a line which is, trying to drive U, and then something else is being trying to drive H. How will VHDL decide whether that particular line will have a value H or mu or whatever it is? So, for example, this will say, well, if 0 and X, if somebody is trying to drive a line 0 also and X also, what will be the value of that line? VHDL will take it as X, unknown. Okay. 0 and 0 makes sense. These are the things that we are comfortable with. 0, 0. Let's see, 1 and 0. Can you see here? 1 and 0. So some gate is trying to drive a line to a value 0, and another one is trying to drive a line 1. It's X here. Okay, X was what? Forcing unknown.